All right, hello students. I had some of you ask me about creating your own exponential word problems or creating your own quadratic word problems. So in this video, I'll focus on creating your own exponential word problems. The key thing to think about with exponential word problems is the equation we use is y equals b times m raised to the x. And if I'll add some sliders, I think this will help you understand what's going on a little bit more. The letter M determines how quickly your graph goes up and to the right or if it goes down and to the right. To be a little bit more specific, the letter M determines how much higher your y value gets for every step to the right. So when an M is equal to 2, that means every step I move to the right, my y value is twice as tall. So you see how 2 steps to the right, it's 4 times as tall as it started. 3 steps to the right, it's up at 8, etc., etc., etc. The b value is the y-intercept. So if I make b equal 0.2, now the y-intercept is 0.2. When I'm at x equals 1, I'll be at a height of 0.4. When I'm at x equals 2, I'll be at a height of 0.8, etc., getting twice as tall because my m is 2. You can see that as the m gets bigger, our curve gets steeper. And if I make the m into a fraction, then my curve becomes exponential decay. One last thing is that we only think about positive values for m and b in our unit. We didn't study anything with negative values because the situation just gets a lot weirder. So when you're trying to come up with exponential word problems, some things you want to be thinking about are, can you use words like doubles? Can you use words like halves or triples or thirds? So some things like that could be if you're talking about cell growth. When a little baby organism is born, whether it's a human or a plant or a fungus or something, usually starts with a very small number of cells that divide in two. And so you could talk about maybe a baby is born, and then after a few weeks, the baby has a couple hundred cells, or that would happen quicker. Let's just say that it only has a couple hundred cells a few days into it, and then they divide every couple hours. Well, then you have a word problem there where you're talking about the number of cells that are in a baby. So you could talk about that. Let's put some numbers on it that let's and I don't know if this is biologically the right number, but we're just going to go with it for the purposes of this video. We'll just say that um, a day after fertilization, there are 300 cells that double every hour. And so then we can write a word problem like, when will there be 1 million cells? And so in that case, we would be changing our model to be y equals, it started in this word problem with 300, it doubled every hour, and we want to know when it gets up to a million, so we can go y equals a million, and then we're obviously going to need to zoom way out. Faster way to zoom out would be to just click on the little wrench up here and make my y-axis go up to a little bit more than a million. And we can see where they cross. There we go. That's where they cross. And so it looks like it takes a little bit under 12 hours. Wow, that's really fast. So that is probably not biologically accurate for how quickly cells grow. But that gives you the idea of how you can write an exponential word problem where you're telling me a starting amount, that's the b, and you're telling me how it changes, and then you're telling me a target number. Another possible idea for a word problem exponentially is something that changes at a percentage rate. So you got something that gets bigger by a percent or gets smaller by a percent. I'll use gets smaller by a percent. So usually, for example, if you buy a new car, it gets less valuable over time. So let's say that a car costs, let's say it's like a $24,000 when you buy it new, and loses, let's say it loses 8% value each year, and we'll give a target number. When will it be, let's just say 10K. And I'm going to go back to default zoom here. So you got a $24,000 car when you buy it. So that's going to change my target, my starting number, my B value, 24,000, and it loses 8%. So I'm going to put in here 0.92. And you might be wondering, wait, where's the 8 involved there? And the idea is that if you take 8%, it becomes 0.08. And if you lose something, you are subtracting it off of 1, meaning you are keeping 92%. So this is the original value. This is the loss, lose 8%. And then this is 92% remaining. Okay? I'm going to pause this for a second. Okay, sorry about that. So noticing here that we have a multiplier of 0.92 for an 8% loss. And then just let's try to find it. So let's zoom out on the graph here until we see up to 10,000. Okay, so that was, again, we probably could have just adjusted with the gear. And let's see, maybe I will zoom in a little bit more on it. Cool, so right there's the point of intersection. So it looks like it's 10 and a half years, right on the dot. So that's kind of, I think that's a little bit surprising that in 10 years after you buy something, it's worth $24,000. It can drop down to such a small value. So I just gave you an example of an exponential growth problem, an exponential decay problem. You could write a couple more of your own. In the next video, I will do quadratic word problems. Just remember with exponential growth, it's always multiplying by the same amount each time, and it's either multiplying and getting bigger or multiplying and getting smaller. And so doubling, tripling, or changing by a percent, that's the way that you come up with exponential problems.